Hello everyone, welcome back to my channel. Today we're going to work through this problem of fluid mechanics. First, let's read through the problem. A wall consisting of a straight vertical section and a half cylinder section is submerged in water as shown in the following figure. The wall has a depth W into the page. A. Determine the resultant pressure and force in the horizontal direction, both the magnitude and direction, acting on the entire wall. B. Determine the resultant pressure force in the vertical direction, acting on the entire wall. So first, let's draw more clearly what this diagram is saying. So basically, we have a wall, and within the wall, there's a cylindrical section. And then we have the bottom of the tank, I guess, that this wall is on. And this wall has a cylindrical section as such, and a wall. And the water is filled up to a level of such, and the triangle over here represents the free surface. And for part A, we will use the principle that um yeah, so we'll take the so basically for hydrostatic pressure in the horizontal direction, the horizontal force is the force of the pressure of the water on the vertical projection of the area. And this is specifically for curved surfaces, I believe. So in the horizontal direction, the horizontal force is the force of the pressure of the water on the vertical projection of the area. And the vertical projection of the area is formed by the straight vertical section and the half cylinder section. And this projection is a rectangle. Basically, we want to know what the projection of this area is. And as you see, it is a rectangle because if you project this area onto a surface, it's going to look exactly like a rectangle. And this rectangle has a width of W because it says that the wall has depth W into the page, and it's going to have a length of H. So um, the vertical projection of the area is equal to W times H. And the pressure on the horizontal surface, since in the horizontal direction, the pressure is equal to the pressure of the water on the vertical projection of the area. We will have that pressure equals P equals rho, which is the density of water times G times Y, which is basically the depth of the water. And let me see. The the pressure the pressure acts at the centroid. So Y is going to be the centroid of the vertical projection of the area. And the vertical Y is the centroid of a proj vertical. And the centroid of a rectangle of width W and height H occurs at distance of H over 2 and width of W over 2. So this means that the pressure is equal to rho times G times H divided by 2. And so we want to know the resultant pressure force. Force is equal to pressure times area, and this is in general form because pressure is equal to force over area. So since we know that the pressure is rho G times H over 2, we know that the force is just going to be area times that value. And we use the same area, which is the vertical projection of the wall of the cylinder. And that vertical projection is simply a rectangle of area WH. So force is equal to thus rho G times H over 2 times the A punch vertical equals rho G times H over 2 times WH. Um, However, as a force, and since we're defining the positive x direction as to the right, um, we'll define positive as x to the right and y upwards. So since the positive direction is to the right, and the resultant pressure force from the water is actually pointing to the left against the wall, we are going to reverse the sign of this force. So this means that the force horizontal is equal to negative rho GH squared over 2W. And is pointing in the x direction, so we add an I hat. And this matches the given answer. An alternative method that we could have used is integration. We could have also integrated. And if we integrate, we will get that force is equal to the integral of from 0 to h of rho g times wy dy. And this will be equal to rho g h over 2 h times w. And this will also give us the horizontal force is equal to negative rho g h squared over 2 times w. And why do we integrate in this way? So let's break it down. We have this rho g, which is the specific weight. And that is specific weight. And it is very common. It's always used in hydrostatic pressure analysis. And W is the width of the wall into the page, and Y is going to be the height of the wall. So basically, this is Y. It basically denotes a distance from the bottom of the tank. And basically, what this is saying is we um is it's another way of saying pressure times area, right? So um a differential area dA is going to be equal to W times dy because we can divide this into very small strips. And if we do so, each of these small strips will have a differential area dA, and the height is going to be dy, but the width is going to be W. So it's going to be equal to W times dy. However, where we now know where these two terms come from, so where does the y term come from in the rho gy? So rho gy, well, this is just the classic expression for hydrostatic pressure. The density of the liquid and gravity is always going to be there. And the y represents the depth because hydrostatic pressure is a function of depth. The deeper you are, the higher the pressure. For instance, the pressure at this location is going to be far greater than the pressure at this location because at this point over here, the column of water above this point is much less than the column of water above this point. So this is why the deeper you go, the higher the hydrostatic pressure. And depth is represented by Y. So this is Y, pun intended. So let's call this method one. Um, and let's call the integration part method two. Now there's also another method that I'm going to go through right now, and it's from considering a control volume, which you're going to encounter very often in fluid mechanics. So let's draw a diagram of the setup down here below. So the resultant pressure force in the horizontal direction acting on the wall is most easily found by balancing horizontal forces on the control volume. So we choose this one. Wait, let me use red to make it more apparent. Yeah, so let's choose our control volume to be this one. It's called our control volume. So we want to balance the horizontal forces on the control volume shown in the figure. And so this is our free surface. Let's draw the free surface. And the distribution of the pressure force along this control volume surface is going to look something like this. Classic hydrostatic pressure distribution. And basically, FH is the horizontal, we're going to call FH the horizontal force that the wall exerts on the control volume. And this horizontal force acting on the control volume will have to equal the resultant pressure force in the horizontal direction acting on the wall. So basically, the sum of the forces in the x direction have to be equal to 0. And it's equal to the force, the horizontal force the wall exerts on the control volume, minus the resultant pressure force in the horizontal direction acting on the wall, which is 1/2 rho GH squared W, as we found in this previous example. However, yes, and that's why it's found by balancing horizontal forces on the control volume, because this control volume allows us to treat again the area as a horizontal projection. I mean as a vertical projection. So again, this horizontal force has magnitude of 1/2 times rho g h squared times W, and it acts on the left, it acts to the left. Um, yes, FH is the horizontal force the wall exerts on the control volume. So the force that the control volume, wait, yes, the force that the pressure force acts on the wall, it's going to point in the negative direction. So it's actually going to be negative 1/2 rho GH squared times W, as we found in all these previous examples, previous steps. So let's call it method 3. Now, what is the control volume? You guys might not have heard of this before yet, so let's go over what a control volume is quickly. So basically, in fluid mechanics, a control volume, or CV, is a specific region in space chosen for analysis, which may be fixed or moving, but its boundaries are defined by a control surface. It is an open system concept where fluid mass can enter and leave, allowing engineers to apply fundamental conservation laws, such as mass, momentum, and energy, to understand the overall behavior of the fluid passing through the region. Um, I'm not really doing engineering, but I'm just taking this course for fun. Mm, and it's actually for another application, but not for my because I'm not getting a degree in engineering. But it's still good to know. Um, so the key concept is that is a control surface, which is the imaginary boundary that encloses the control volume, and that it is an open system. So the control volume approach is considered an open system because mass can cross its boundaries. Conservation laws. The analysis of a control volume focuses on applying the principles of conservation of mass, momentum, and energy to the fluid as it flows through. So how it works, define the control volume. An arbitrary region in space is chosen which could be stationary or moving, and its surrounding boundary is defined as the control surface. And next we apply conservation laws. And next we analyze inlets and outlets. And next we solve. And why it's used is that it simplifies complex flows, because instead of tracking individual fluid particles, this method simplifies complex continuous flow problems by focusing on the system as a whole. And what are the applications? It is widely used in engineering to study a variety of fluid mechanics and thermodynamics problems, from flows through nozzles to the performance of turbines and pumps. Let's look at a few images. So this is like the system boundary, and then we have system and gas. So in fluid mechanics, we have to select a region that simplifies the analysis by defining boundaries where flow characteristics are well behaved and easy to describe, such as straight and parallel streamlines at inlets and outlets. The goal is to use a control volume that minimizes the complexity of evaluating fluxes across its surface, often by ensuring streamlines are perpendicular to the control surface. The choice of control volume depends on a specific problem and the desired outcome, with different choices possible for the same problem, though the final answer should remain constant. Should remain consistent. So steps for choosing a control volume. Understand the problem, identify the unknown, and draw the control volume. Align with flow. Minimize unknown fluxes. Include necessary structures. Apply conservation principles. Evaluate consequences, and consider different choices. Yes, so in this particular problem, this was the control volume we chose. And sorry, the control volume extends a little too far. I meant to draw it only like this, only here. And yeah, so let's move on to part B. Part B says to determine the resultant pressure force in the vertical direction, magnitude and direction acting on the entire wall. So B is more complicated. So basically, for part B, we know that the vertical force on a curved surface can be represented by the weight of the volume of water above that surface. So, this will come in useful later. But first, let's analyze what the forces are um, on our chosen kind of segment of control volume. So basically, oh yeah, our semicircle structure looks like this. Let's call this point E. Let's call this point A. And oops, wait, hold on. Yeah, so by the way, A is if you draw it down like this, so A and this C, and this one is D. This one is B. This one is E. So if this whole area were filled with water, it will look like that. And basically, it will exert a force on CD. And this force on CD is actually equal and opposite to, let me see if I can copy and paste. To basically the force on the bottom on CD. Which is the force of this volume of water over here on CD. So these are equal and opposite. Basically, this region over here and the force it exerts on CD is equal and opposite to this little volume of water and the force it exerts on CD. And basically, and here's a nicer drawn out diagram that I created. So basically, if this whole area was filled with water, it will look like this. And if the area below CD was filled with water, it will look like that. And these two forces are equal and opposite on CD. Um, and basically, um, this force acting upwards over here, it is acting upwards on CD. Uh, it basically represents this force over here, but we represent it as a force upwards, but of the same magnitude as the volume over here exerts on CD. And if we add basically this force on CD and this force down on BC, we have that the force in the middle must balance those two out because essentially this whole equation over here is saying um, if you had this volume plus this other volume over here, basically the forces associated with those volumes, then we see that it's equal to this volume over here. Basically, if we shade everything here. But thus the force of in BCD, the cylinder must balance these two forces out. This upper force and then this force pointing downwards. So the force in here must balance those two forces out. And what this is saying actually is can be a little tricky to understand, but essentially this force is equal to this force over here. They're both pointing upwards. And basically we showed that we showed previously in this diagram that the force associated with this volume must equal the force associated with this volume, even though the volumes are really different. But the magnitudes are the same. So reversing the direction of the arrow to point upwards will give us the same force and same direction as the force exerted by the volume of water beneath CD. So going back to a problem, we know that the vertical force on a curved surface can be represented by the weight of the volume of water above that surface. So we can consider volumes. And so the vertical pressure will be equal to um basically the kind of weight of water inside this cylinder. Basically, this cylinder looks something like this, and it contains some volume of water, and it has a radius R and a width of W. So already we know that the volume is equal to the area of this semicircle times the depth, which is W, which is equal to pi R squared over 2. That's the area of the semicircle times the width of the cylinder. This will give us the volume of this half semicircle of this like semicircular volume. And we this gives us the volume, and volume times rho will give us volume times density will give us the mass. So the mass will be equal to this volume, which is pi R squared over 2 times the width, multiplied by rho, which is the density, which is mass over volume. So this is mass. And then in order to get the weight of this volume of water, we multiply by gravity. And thus the vertical pressure will be equal to this pi R squared over 2 times W times rho G in magnitude. However, it'll be pointing in the negative direction because we want the resultant pressure force in the vertical direction acting on the entire wall. So this force is going to be pointing downwards. And because it's pointing downwards, it's going to be negative. So That's why we add a negative sign here. Now let's backtrack a little and think to ourselves why we just calculated the weight of this volume of water in order to get the vertical pressure acting acting on the entire wall surface. Well, first of all, we know that the first horizontal portion, or I mean the first vertical portion, this portion will not have a vertical pressure associated with it because the vertical force or the vertical pressure will be parallel to this wall segment. However, on this semicircle area, there will be a vertical pressure. So that was the section we calculated the vertical pressure for. However, remember what we just said. The vertical force on a curved surface is represented by the weight of the volume of water above that surface. This is a little misleading because it's also accounted by the weight of the volume of water below that surface. So as we saw previously over here, um, the basically the weight of the volume of water above and below the surface of this wall, because the wall is actually semicircular over here. So if you consider the weight above and below, and the weight above and below is equal um to this whole volume. And this whole volume will be the weight of the volume of water above that surface. And basically, this weight of water above that surface is equal to kind of the weight of water inside um this semicircular volume because of how the forces actually balance each other. Because as we saw previously, you guys can rewind to that section. The pressure and the force in here must balance out these two pressures. So because they must balance out, the magnitude is equal to each other. So we can simply calculate the weight of the volume of water in this semicircular area, this semicircular volume. Another easier way to understand why it must be is we use buoyancy. So basically, as I mentioned down below here, by the buoyancy force, the volume of water displaced by the semicircle can be used to calculate the vertical hydrostatic force. Because basically, what buoyancy is as we see over here, the buoyant force is an upward force exerted by a fluid that opposes the weight of an immersed object. And Archimedes' principle states that this buoyant force is equal to the weight of the fluid displaced by the object. This principle explains why objects float or sink with a lower density object floating because the weight of the fluid it displaces is greater than its own weight, and a denser object sinking because its weight is greater than the buoyant force. So there you have it. So another simpler way of thinking to arrive at this same conclusion that the vertical pressure must be equal um to what it is over here, which is this value over here, is by thinking about buoyancy. We know that the semicircle portion is submerged. We know that it is submerged and that it displaces a certain amount of water since this portion is empty space. And the amount of water it displaces must be equal to the buoyant force. So if you think about that, this is why the resultant pressure force in the vertical direction acting on the entire wall is equal to the weight of the water that this semicircular portion displaces. Because again, if there was no semicircular section, it would just be a vertical wall and there will be no vertical force. However, since there is this semicircular section, the only difference is that a certain amount of water is displaced. And since a certain amount of water is displaced, um, there is a buoyancy force associated with it. And since the semicircular section exists and that it displaces this amount of water, um, there is a vertical force associated with it. So that vertical force must then be equal to the buoyancy force, which is equal to the weight of the water um, displaced by this semicircular section. And it is basically pointing in the j hat direction, so don't forget that part. So you've now seen two different ways of thinking through this problem. I'm going to offer to you another way of thinking about this problem, part B. So we can also consider control volumes as we did for part A. And over here, since the vertical portion does not have any vertical forces, since the vertical pressure force will be acting parallel to that surface, we'll only consider the control volume starting from here. So only the semicircular portion. And on this semicircular portion and on this control volume, so the control volume is like this, there will be some forces acting on the fluid in the control volume. And these forces are Fv, the vertical force of the cylindrical surface on the volume of fluid, and also the force downwards. And we'll also have the force yeah, so Fe is the vertical force the cylinder exerts on the control volume. And we also have resultant pressure forces acting on the top and bottom of the control volume. So we will call this first force distribution F P comma T. So Fp is just the force from the pressure. And we also have the same thing on the bottom. So which we'll call FPB, the pressure force, the resultant pressure force acting on the bottom of the control volume. And W is the weight of water in the control volume, which we will call W. And W stems from both of these volumes over here, which I'll shade in green. And I'll underline it in green too. So we want to balance forces now on the control volume. So the sum of forces in the y direction will have to be equal to 0. because it's in static equilibrium, and it's equal to negative FV plus FPT minus FPB plus W. So the force from the pressure at the top of the control volume can be represented as rho times G times H, which is the whole height of the wall. So H minus 2R, which is this distance over here. And why we subtract that distance is to get this distance up to the control volume surface. So from the control volume surface up to the top is H minus 2R. So that's why rho G times H minus 2R. And then we want the horizontal projection of the area, which is going to be RW. Yes, it's going to be RW because looking at this from the top, the horizontal projection of the area is going to be R and then W. So the area is RW. And FPB is equal to rho GH times RW. Because at the bottom, the distance from the bottom of the control volume to the top is H. And the horizontal projection of the area is also RW. Now we have to find the weight of the volume of water in the control volume. So how do we do that? We can express it as rho, the density of water times gravity, times the volume of the control volume. So what is the volume of the control volume? We can express it as basically this rectangular portion, the volume of this rectangular portion, minus this cylindrical kind of component. Yes, so this like box, this volume of the long box minus the volume of the cylinder of the cylindrical half cylinder volume inside. So first we want to find the volume of this box. Well, one side is going to be R. The other side is going to be 2R. And this whole thing is W. So then we have the volume is equal to W times R times 2R, which is 2R squared W. So 2R squared W, sorry, R squared W. And then we subtract the volume of the half cylinder volume inside. And that volume is going to be pi R squared over 2 times W. So minus pi r squared over 2 times W. That's going to be the volume of the of this green area. So now we have the volume of the control volume. We can plug it in for VCV. Basically, this will give us rho G times r squared W times 2 minus pi over 2. And this will be the weight. So now we have the whole expression for the force balance. So equal 0 is equal to negative FV plus rho G H minus 2R RW minus rho GH times RW plus rho G R squared W times 2 minus pi over 2. And now we can solve for FV, which is the vertical force on the cylinder exerts on the control volume. And this vertical force that the cylinder exerts on the control volume will be equal in magnitude to the vertical force on the wall, on the cylindrical portion of the wall, which is equal to the total vertical force since there's no vertical force on the initial vertical portion of the wall since the vertical pressure force will be parallel to that wall. So Fe is equal to uh rho is equal to rho GH times RW minus rho G times H minus 2R times RW minus rho G R squared W times 2 minus pi over 2. And if we simplify FV, we should get that FV is equal to negative pi over 2 rho G R squared times W. And thus, the vertical force on the control volume acts downwards with a magnitude of pi over 2 rho G R squared W, since the assumed direction was upwards, but the sign is negative. Thus, the force acting on the cylindrical section acts upwards with a magnitude of pi over 2 rho G R squared W. Yes, so the force on the cylindrical section acts upwards with a magnitude of pi over 2 rho G R squared W. And yes, I guess here the negative sign means it acts upwards since the downwards position was defined to be positive. Let me verify. No, sorry. Actually, that is an incorrect explanation. So actually, the reason why the vertical force acts upwards is because we assumed the FV to be upwards, but we actually got a negative answer. So this means that the FV is actually pointing downwards. It actually means that FV is pointing downwards. And FV is the vertical force the cylinder exerts on the control volume. So if the force that the cylinder exerts on the control volume is negative and pointing downwards, this means that the force of the pressure force on the wall, on the cylindrical portion of the wall, must point in the opposite direction, and opposite direction of downwards is upwards. So that is why the force acting on the cylindrical section acts upwards with a magnitude of pi over 2 times the rho g r squared w. So our final answer is actually over 2 rho g r squared w upwards. Yes, it can get confusing. And another alternative approach is to integrate. And here's a little example of how to do that. I'm not going to walk through this part by myself right now, but you guys can feel free to go over it and make sure you understand it for yourself. Thank you guys. I'm gonna go back to the problem. So this one was a long problem, mainly because we went over many different methods to solve the same problem, but I hope it was helpful for you guys all. And don't hesitate to message me with questions. I'm going to be posting the slides into discussion as usual. And see you guys in the next video.